Okay, it's just starting. Thanks. Okay, good afternoon. Welcome to 240. So first of all, the first homework is due, and I hope you had some fun with it. I've seen some. It's really only one page, and then maybe one other page for SPICE results. Of course, I will post the solution. So if somehow you found it very complicated, maybe you can get sort of the knack how to do that with the solution. And if you still have questions, please come and ask, because it's important that you sort of subscribe to this idea of using GM over ID, essentially, right, to design stages. The minute you sort of go back to the square law model, and I had lots of discussions in office hours of sort of attempts to do that. The minute you do that, you sort of open the can of worms for all the types of problems that you get from discrepancy of that model with real devices. Okay. Are there questions that you want to ask right away or so? Okay. Then one other thing that I would like to quickly go over is last time I got a few questions about gain. And so this is still concerning lecture 3, gain. And so we really have two definitions of gain. One of them is the small signal gain, AV equals dV out over dVi. Right? And then the other one is kind of the large signal gain, and that would be V out over Vi. Okay? And I had plotted these two gains for a common source stage, and they looked something like that here as a function. I plot them usually as a function of V out instead of as a function of V in. Why? Well, because most of the time the amplifier really has a high gain, and then V in would be there 5 microvolts, and V out would already be 1,000 volts, right, or something like for VDD. So V out is usually the better parameter to use on the horizontal axis. And so here are these two gain metrics. And so there was the open loop, the small signal gain, AV like this. And then there was also the large signal gain that looked something like this. Something like that. That was AV. And actually, the large signal gain was kind of wrong, because as some of you pointed out after the lecture to me, at some point, at the bias point, if you want, the small signal and large signal gain should coincide. And so, really, the way we should calculate this thing is AV equals V out minus V out 0 over Vi minus Vi 0. So there, in other words, there is one point where, let's say this, where which we call V out 0, and there is also corresponding, not on this graph, right, but the corresponding Vi that I need in order to get this V out. And that's my bias point. And then if I evaluate the gain at that point, the large signal and small signal gain are going to coincide at that one particular point, right? And then as I deviate from there, they're going to differ again. You have a question? Okay. So the reason I got this huge discrepancy here is I didn't really do this. I didn't subtract these numbers, and I replotted. I redid the slide. So this time I have I chose V out minus 1.542 volts. You don't need to write this down. It's just that for that particular circuit over Vi minus 820 millivolts, and then this is now this bias point where they coincide, right, somewhere here. And then indeed at the bias point I get agreement between small signal and large signal gain, and elsewhere they don't quite agree. Okay? Now, most of the time, this is not a problem at all, because most of the time we use fully differential amplifiers, and then these two numbers are 0, and you don't need to fuss with all of this thing. Right? That's precisely the reason why we use differential amplifiers, because then they don't have a built-in offset, right? At least not beyond the random and device mismatch and so on offset, right? Systematically, they are designed for 0 offset. A common source amplifier, of course, is not. And because here I wanted to make a simple example, I use the common source amplifier, and then we run into this complication. So sometimes simple means complicated. Okay, so most of the time that's not going to be a worry. Notice, however, that my main point that I was trying to make, or one of the points I was trying to make, is that the large signal gain here really has a much larger span over which the circuit has high gain than the small signal gain. So that's still true. And I guess by analyzing the function, so we could probably find an explanation why this is the case. Okay, so new topic, electronic noise. I've given a motivation for why we should deal with noise, and take it or not, you are in this course, so we'll talk about noise now. There are, if you can use a little more Zoom, please, thanks. There are quite a few topics. It's not very complicated, but somewhat tedious area, and so there is several perspectives that we're going to use when we talk about noise. The first one is just the noise phenomena, just sort of what is it, what's the physics behind it, and so on, a little bit, right? And how do we describe it, statistics, and so on, right? Then we are gonna zoom in and say, well, I mean, actually, thermal noise, which is the main form of noise we're going to talk about. You can go to mechanical engineering, take a course there, and it's about thermal noise in beams and bridges, and probably not bridges, because even though it's there, it doesn't make them vibrate a whole lot, right? They're too heavy. But so it doesn't really matter what the domain is. We are going to focus here, of course, on the electrical domain, so noise in transistors and resistors and stuff like that. And then an very important part is that if we've built this circuit with hundreds or maybe even thousands of transistors and maybe a few resistors and capacitors, and then of course all these devices, they somehow have noise, right? And using what we know about device noise models, we can calculate that. The trouble is that it's really not very interesting, right? What we want to know is, how does this noise affect the performance of the operation of our circuit? And that, again, depends a little bit on what we want to know, right? In some cases, we want to know one thing. In other cases, we want to know another thing. And so we're going to talk about a whole slew of how we can express the noise of a circuit so that it's going to be useful when we're using or specifying or whatever this circuit. One common thing that you may have seen is when you look at the operational amplifier data sheets. Download one from the web, Maxim or National or ADI, whatnot, right? Then you will see that there is a specification on noise, and it says, it's usually called something, the wording may change, input referred noise. What does this mean? Well, what it means is that they, instead of telling you, okay, look, this is exactly what I've put into my amplifier, and it's very complicated, right? And most users, of course, would be totally lost with that. They say, look, my amplifier behaves like a totally noiseless amplifier, and just at the input, I have a noise source, right? So I can model my amplifier as an ideal amplifier with at the input some noise. And this noise at the input makes up for all the actual physical noise sources that are really present in that device. That's very useful when you sell an operational amplifier, because engineers then know how to take this fictitious noise source and calculate the overall noise performance of the circuit they are building with this operational amplifier. And then there are other cases when you build an RF front end and so on, and then you want to use a different kind of characterization of noise, for example, noise figure and so on. So we're going to look at a whole bunch of different representations of noise. It's always the same thing, but it's put into a different form so that we can use it to answer the questions that we happen to have in that particular circuit that we are dealing with. Then we are going to look. When digital folks, they don't usually talk about noise. They talk about bits. But it has kind of a similar effect because no computer has an infinite number of bits, right? Maybe 64 or something like that. Well, that means that if you take a value, a real fact, let's say Boltzmann's constant, right? Then in the computer, it's represented as an approximation. It's got only 64 bits. Honestly, admittedly, it's very precise, right? But it's not perfect, right? Or pi, it's never accurate in the computer, right? So we're going to use that to relate circuit noise, thermal noise, to bits, so that we can say, well, this circuit, it has so much noise, that means it performs as it had 12 bits, right? As if it was a digital circuit that used just 12 bits, right? And so that's going to be a very nice benchmark because, of course, bits we are very familiar with, all of us, right? And very often also there is some analog circuits, and then ultimately it's actually going to be bits. Well, there's no point on using a 32-bit DSP if the stuff that goes into it really has only 8 bits worth of real data and the rest's noise, right? And then in the end, and that gets back to my motivation for why we talk, or one of the motivations why we talk about noise, we're gonna relate noise to power dissipation. Turns out that if you want to have a circuit that has little noise, a large number of equivalent bits, then probably you're going to have to put a lot of power into it, right? And of course that's important for obvious reasons. Okay, so if you get confused, well, what the heck is it that we're talking about? Well, it's still noise, but we're somewhere on this schedule, and maybe turn back to this and figure out where we are. So, okay, so first, there are really several types of noise, and one of them here I put down as interference or so. Noise, of course, is not exactly an engineering term, and even less a term that has been invented and is reserved for analog circuit design. So it's used for all sorts of things. And sometimes even more generally, we talk about errors, right? And so we need some kind of a classification just to be sure what we are talking about here. So interference is one kind of noise that very often is a real issue in circuits, and we have to deal with. One form of interference is signal coupling. You can have capacitive, inductive coupling, and so on. If we talk about an analog IC or so, where do you think is the biggest problem of coupling signals around? You've made an IC and you have lots of signals, right, and you're worried about them coupling to one another. Where are you going to look first? Well, interesting enough, first you probably have to look in the path frame. Bond wires, they make a couple of bond wires, even if they're relatively far apart, they don't make a very good transformer, but if you want to keep things apart, they're a ridiculously good transformer, right? So the number one culprit usually when you have signal coupling is actually the path frame, okay? And we'll talk about that later, but I just mentioned this here, so remember that. Very often we're going to talk about other forms of noise now, right, for weeks. And you're going to build an IC, and you're going to do all of this, right, because I'm going to flood you with that thermal noise business, right? But then in the end, the actual problem is perhaps going to be an issue with the path frame. You put bond wires too close to one another, so okay. So, of course, long buses also can couple capacitively and so on. Supply noise, obviously, right? I mean, that's again a thing like in SPICE. In SPICE, the ground node, right? We make node 0, and it's supposed to be quiet. In fact, if you build a digital processor, a CMOS processor, Pentium or so, how much do you think ground or VSS is going to bounce up and down as this thing is running? A millivolt? A microvolt? Unmeasurable? Any ideas? Just rough. I mean, it doesn't have to be accurate. Just within 3 orders of magnitude. Okay? Yeah.
30 millivolts?
Then you do very, very good if you can do 30 millivolts. Usually, very often actually, you turn on junctions. It's so much. So it's several hundred millivolts often. And of course, you don't try to not turn on junctions too much because of all the current that flows. Right? But typically several hundred millivolts. So really not ground in the SPI sense. The same thing with the supply voltage VDD. VDD is not going to be 3.3 volts. It's going to be 3.3 volts with lots of spikes and droops and so on. Right? And there are a bunch of other, we can imagine other reasons, right? The lights coupling. Yeah, sometimes when you go to a lab, you see a dark cloth draped over a chip. Well, why is it? Well, because of the photo effect, right? If you have exposed junction, you generate electron hole pairs, and they add extra current to your signal that you probably wouldn't want to be there. So sometimes engineers work in dark, on the dark cloth. Okay, so these are very important forms of noise, and very often they are really the culprit on why stuff doesn't work, right? There is nothing particularly fundamental about them. If we do everything right, I mean, we use shielding and so on, in principle at least, we can always beat down these forms of noise, right? We can use more blocking on our power supply. We can use separate power supply for the digital and the analog ports, even maybe several power supplies for different parts of the analog circuits. And there are lots of ways we can deal with them. It's very important. One other thing, and I'm maybe a little bit too honest here, is that there isn't a nice theory or so that governs these. It's engineering, right? We need to go over all these problems and find them and solve them on a case-by-case basis. Okay. So there is another, and we'll talk about some of these in more detail, but now we're going to talk about noise that is more fundamental and created in our devices. Most forms of this device noise are going to be caused by the discreteness of charge. Right? Either you've got an electron or you don't have it, and even though an electron has a small charge, it is noticeable. Right? And when they bounce around, well, they produce noise. There is one absolutely fundamental part of this noise, and that's called thermal noise. And it's unescapable, and sort of the physicists bestowed it on us, and we can calculate exactly what it is. And you can be as clever as you want, but if you build a resistor, it's going to have a certain amount of thermal noise, and you can't make it better. Okay, and then there is another, and so that's the most important form of noise that we're going to talk about here. And again, I mean, in this category here. So there are other noises that are just as important, but now we're going to concentrate on these. The other one that we'll talk a little bit about is flicker noise, and that one is not fundamental. It depends on the technology you have. Some of them are better, some of them are worse, and so on. We'll see. Fortunately, there is here, even if the technology isn't stellar, there are ways on how to circuit techniques, how to get rid or at least reduce flicker noise. In thermal noise, it's more complicated. You can do it sometimes, but if you try to get rid of noise here in thermal noise, usually means more power. Okay, and you don't really get rid of the noise. You just make more signal or so. Okay, so with that. Let's start looking at the phenomenon of noise, and we look at noise in the context of a resistor. So the origin of this noise is really the electron. So if you look at the current flow, then if you looked into a wire and we had some kind of a microscope that would allow us to see individual electrons, then of course if you have an electrical field here, then these electrons are going to They're going to flow with the field, right? They're going to travel with the field or against the field. But they're actually not going to do quite that. They're also going to bounce around. They're going to bounce around actually in a rather complicated way, such that the net effect is that they go with the field, but in reality they jump around quite a bit. And even in fact, if we didn't apply any field at all, and we were to make a barrier here, and we were to count the number of electrons that cross this barrier, we would see that it's not zero, even though there is no field applied. But there are constantly electrons that bounce from this side to the other side of the imaginary bound and back and forth. And over a long time, the mean number of bounces in the two directions is going to be zero. But over shorter time, there is always going to be a little bit more on one side and then a little bit more on the other side. And consequently, if then you were to use an oscilloscope across a simple resistor, then you would see on the oscilloscope screen this fuzziness and so on. That I'm sure you have seen before. Right? That's really these electrons that are bouncing around. Temperature is the source of energy. So if you cool it down to absolute zero, then they won't do that anymore. But so you probably won't be able to observe anything anymore either. So. Okay, and so then there are the usual examples. If you put ink in water, you see exactly the same thing. Then it's called Brownian motion. If you do the exact same thing with electrons, then it calls Johnson noise. Right? But it's really the same phenomenon. And in thermodynamics, it will refer as the same thing. Okay, so now there is one problem with noise off the bat, of course, and that is that normally when we analyze circuits, we want to know what is the voltage in every node. Well, when it comes to noise, we cannot possibly know what is the voltage in a particular node. It changes all the time, right? It's random. So instead of really using voltages or currents with noise, we use statistics. More precisely, we're going to use power of the power of the noise to figure out what it is. So and then there comes this thing that usually referred to as the equipartition principle, that says that really the noise available per degree of freedom is kT times the bandwidth. Noise is distributed over frequency, right? And so the wider a band we have, the more noise we get. Okay. So available noise power simply means, or this kTb simply means this is if this is our noisy resistor. This kTb simply means that this is the total power, that the maximum power that is available for this thermal noise power for this resistor to deliver into some kind of a load. Now, to deliver the maximum amount of power, it's relatively easy to show that we need to load our circuit with a resistor of like value. So in that case, we actually have the maximum power that this, and we know that this is going to be the kT times B that is going to be delivered to this circuit. So now we can use the fact that we know R and R here, and we know the total power, and we can calculate Vn. Right? We do that. So the total power then is we know first of all the total power is kT times B, and we also know that the power delivered by this source is Vn square over R, but then that is the power delivered to both of these resistors. Only to this resistor we divide by 4. So this kTb is equal to Vn squared, the power delivered by the source, divided by Vr, 4R. Okay. Now we can solve for Vn squared, and we get an expression for the thermal noise of a resistor, which is 4 kT. And so this is the Boltzmann constant. This is the absolute temperature R is the value of the resistor, and B is the bandwidth. Okay, so that is the now again, because the noise is a random phenomenon, this is not really the noise voltage across the resistor, but it is the mean square value, or power, if you want, the expectation of the voltage, noise voltage across that resistor. And so the unit of this thing, consequently, is V square, right? That's not just V. Okay. This equation here is marked in red because it's one of the few equations that you will actually have to learn by heart. Yeah. The noise is generated by this resistor. This is just to make this resistor here, just to make sure that we transfer the maximum amount of power. And we get that by making these two resistors equal. So this is just a measurement device, if you want. Okay. Okay. So thermal noise. First of all, what sort of exhibits thermal noise? Well, all dissipative elements, all elements that can dissipate power. So that immediately accounts for resistor, probably transistors, because they occasionally get hot. Probably not capacitors, and we'll talk about that in a moment. So again, the voltages, they're really random fluctuations, and we can't know what the voltage is at any particular instance in time, except if we just happen to measure it then, but next time it's going to be different. And it's also totally independent of current flow, right? Whether we apply a current to the resistor or no current to the resistor, we pretty much get the same. Okay? And so it's characterized by, first of all, this second movement, right? The power. And it's funny. We talk about power because of this picture here, right? It's really power that is delivered to the load, and the amount of power is kT times B. But it is more convenient to actually work with these units of volt square, and we always can convert to the power simply by dividing by the value of the resistor R. Then we would get the power. But afterwards, when we do noise calculations, then really this formulation is more convenient. So we refer to this and we say it's power, but it's actually got units of volt square. The noise has zero mean. That's a good or bad thing. Otherwise, you would have a perpetuum mobile, right? Constantly, we could harvest this noise power, and so that also sort of means something for nomenclature. If you accidentally forget the square, you write this, then this is going to be 0. Or if you accidentally write this, then of course this is 0 squared is also 0. You really gotta write it like this, and otherwise it's wrong. And I actually may mark it wrong. Okay. We can model a resistor by its noise voltage. So again, we could use sort of what they do with operation amplifier. We have here the value of the resistor, and we could say, well, this is sort of like an old normal resistor, none of this noise business. We model the noise with a series voltage source, and we don't know the value of its noise source. All we know is that over a long enough time is 0, right? And we know also that V of t squared over a long enough time is going to be 4 kT times R times B, right? We could, and sometimes it's more convenient to represent the noise of a resistor not with the voltage source in series, but instead with a current source that goes in parallel with the resistor, and then simply using Thevenin's equivalent, In square is then equal to Vn square over R square, and that is equal to 4 kb T times 1 over R times B. Okay. So so these two descriptions are really equivalent, and the reason why I put both here is that sometimes you really can save a lot of time calculating if you just use the right one and start. Okay, and then we actually know something about the distribution of the noise. Now, what is a distribution? Well, if we somehow had a resistor and we were to use a fast instrument or whatever, some instrument that measures the voltage all the time, would of course get different values all the time, right? Let's say we measure every microsecond we measure, and we get a different value every time. Now we would plot here the voltage that we got across our resistor, and here the number of times that we got that particular voltage, right? And not too surprisingly, most of the time the voltage is actually going to be very small, 0 or just very small. And then with increasing with smaller probability, the voltage is going to be large. And the shape of this thing is a Gaussian hat function. And it basically says that, look, I mean, yeah, actually this width here is Vn squared, and this square root here. Okay. Okay. And the chance that our noise is within this voltage here, within plus or minus this voltage, is actually about 63% or so, right? Okay. And then there is a finite and increasingly smaller chance that our noise voltage, the noise voltage from the resistor, is much, much larger. In fact, there is an arbitrary small chance that the voltage across our noise resistor is infinite. Of course, we don't need to worry about this. It's still not going to zap us because the power is still only 4 kBT times B, and that is still a very small number. So it's not going to shock us, but instantaneously the voltage could be large. Okay. If we open circuit it. All right, so that's this Gaussian distribution. Then another important thing is the spectral distribution. Well, what is that? Well, if we were to take a spectrum analyzer and the spectrum analyzer, basically what it has is it has a filter, and the center frequency of that filter can be adjusted. And then after that filter comes a power meter, and it measures the total power that comes through this filter that, for example, has a 1 Hertz bandwidth. Right? So what happens if we take a spectrum analyzer, we put it across our resistor, then we sweep it, and we find out how much noise first do we have in the band from 0 to 1 Hertz, and we mark it here. Right? And then we go and measure the amount of noise power that we get, that is from 1 Hertz to 2 Hertz, and we mark it here. And if we do that, we actually find that it's going to look like this. So this is the noise per. So this is Vn squared over delta F divided by our measurement bandwidth, and so this would be actually equal to 4 kB times T times R times B over delta F, this one. Right? So then we get the noise density, and that one has the even more funny units of volts square per Hertz. Okay, so what I've plotted here is actually correct. So this is a function of frequency. For a resistor, for any thermal noise source, the noise is totally independent of frequency. It doesn't matter whether we let's say if we have our ears, then our ears are sensitive from a few hundred hertz up to maybe 15 kilohertz or something like that, right? And all the noise that falls into that band actually can be detected by our ears, and it's gonna make a small amount of it's gonna make some noise. Right? We actually hear that, right? But if we on the other hand, if we had a cellular phone, then it receives at 1 gigahertz, right? And maybe has also a bandwidth of a few 10 kilohertz or whatever at that 1 gigahertz. Well, if the bandwidth is the same for our ear and for that phone, it's going to get the same amount of noise from that resistor, assuming that in both cases it's the same resistor that is the source of the noise. Supposedly, once you get into the terahertz region, something strange happens and the noise actually falls off. I've never been able to measure anything in my circuits up at terahertz, so whatever, perhaps, probably, I don't care. Okay, so noise power that doesn't change as a function of frequency is called white. So that's why we call this noise white. And apparently it's true up to about 80 terahertz. Okay, so one thing that's prominent in there is always this factor KB, and it's 4 times 10 to the minus 21 at actually 70 degrees Celsius. So here it's definitely warmer than this. Very often we use, many engineers, they remember this number, and of course it corresponds to only 17 degrees. That's not why engineers in general like cold weather. So it's simply that then this number becomes pretty round, right? 4 is easier to remember than 4.0763 or whatever it would be. When you actually analyze your circuits, you see now right away, well, if the temperature, right, I mean, my circuit would perhaps run fine at 17 degrees Celsius. At 100 degrees Celsius, of course, I would get extra noise, and then it may not work so fine anymore. That's why in SPICE there is a way to set the temperature, and we have to do that and run it also at the high temperature, and they're probably going to be sort of worst case noise. Let's quickly look at an example of a resistor. So we have a resistor that's 1 k ohm. Let's assume that we are interested in the noise that this resistor puts out in a 1 megahertz bandwidth. Perhaps we hook it up to an oscilloscope or spectrum analyzer that just has 1 megahertz bandwidth. So we have an animal with super ears that has a 1 megahertz bandwidth, or whatnot, right? Some kind of a circuit that has a 1 megahertz bandwidth. You can redo the example. So then we can calculate this noise voltage. Vn square is equal to 4 kB times T times R times B, and this is equal to 4 microvolts square. Of course, it's going to be. We've said before that this has units volt square, and you can figure that out and so on. And I think it's really true. It's going to have volt square. Now 4 microvolts square would actually be 16 times 10 to the minus 12 volt square, right? That's really the result that comes out of this. Now, 16 times 10 to the minus 12 volt square, can you do something with that? Well, me neither, right? It's sort of very hard to get anything useful out of this. So I always pull the square root out of this, and then I get something that has units of volts, and now it's 4 microvolts. Well, that kind of says something, but we still don't quite know what it is. Well, one meaning of this is, if we had a sinusoid and we were adjusting the amplitude of that sinusoid so that our sinusoid produces exactly the same noise power as this 1 k ohm resistor, we would have to adjust the RMS amplitude of our sinusoid just to these 4 microvolts. Okay, so now we have it. In fact, one easy experiment we can do is we can run again, or we can take our oscilloscope, and we put the resistor there, and well, let's put the 0 here, right? So we're going to get fuzz like this, right? Totally random, right? The oscilloscope does it better than I can. Then we put in a sinusoid that, and we adjust the sinusoid's power. We use some kind of a power meter, right? We adjust the sinusoid's power that it is just equal to the power of the noise. Then that sinusoid would be just about equal in amplitude as the peaks of our noise. Sort of, I mean the peaks, right? We know that there's this Gaussian distribution in it. So, okay. All right, so that then would be one interpretation of this 4 microvolts, and that's why I usually say it's 4 microvolts RMS, because it's the noise power is the same as the power from a sinusoid with 4 microvolts RMS amplitude. That's really what this means. Okay, so now so apparently 4 microvolts, right? If I build a sensor that sort of puts out nanovolts or so, then it's probably a problem. On the other hand, if I have something that is in the millivolts, well, then this may not be a problem, right? Source that's in the millivolts. Okay, we of course could also use this equation here, and then we would get something in amps, so nanoamps apparently. And then the last one is just the density. The last number is just Vn squared over B. That's equal to 4kBt times R, and that is equal to 4 nanovolts squared per hertz. Okay, that's the result. And just like before, 4 nanovolts squared, right, would be again, this would be 16 times 10 to the minus 18 volt squared. Come on. In fact, in some version of, I think some versions of the HSpice post-processor, in its infinite wisdom, has a piece of computer code in it that if you plot something and the absolute value of this something that you're plotting is less than, I think it's 10 to the minus 18, something like that, then it says this is, well, it's got to be at least 10 to the minus 18 or so. Well, that's a little problem if you're plotting noise in the V squared form, right? Because then, hey, that's very common. Now, the minute you pull the square root, you get rid of this issue. But so if you use that, or if you see something like that in your post-processor, check whether that isn't perhaps the case that your post-processor is clipping and the noise is actually smaller, but the post-processor insists that something that small cannot possibly be the right answer and consequently adjusts it voluntarily for you, makes it a little bit bigger. Well, thank you very much, right? Okay, so we normally pull the square roots out of this thing, and then we get 4 nanovolts. Now we have this bizarre thing that we have to pull the square root out of hertz, and well, that's the square root of hertz. Right? So we have this very bizarre units for noise, and if you go into your data sheet of that operation amplifier, then lo and behold, it specifies the noise of that operation amplifier in nanovolts per root hertz. And if it has only 4 nanovolts per root hertz, then this is a mighty good operation amplifier, at least for what noise is concerned. More typically, probably will have 20 or 50 or 100, right? Okay.
Excuse me?
Yes.
There's a number 4 before the KB, right?
Oh, yeah. Thanks. Otherwise, it would be only 2. That would be good. I would take it. Thanks for pointing that out. Yeah, so, okay. Well, so that's noise in a resistor. Now, what happens if we have noise in a circuit? And let's thread slowly, right? The first step is we look at noise of a passive network. So the resistor, we've already got it covered. Now, what about capacitors and inductors? Well, those are noiseless. And in fact, it's very easy to show that that must be the case. Let's do a little thought experiment. Let's say we had built this new capacitor, and I don't know why, I guess that's not a particular achievement, but this new capacitor actually was noisy. Huh? So we could model it also as an ideal noiseless capacitor in series with some noise source, Vn squared, right? And then we load this capacitor with another capacitor, right? Maybe of the same value, in order to see how much noise we get. Well, now of course, this noise source here would try to deliver noise to this resistor, to this capacitor, and consequently this capacitor would get hotter and hotter, and because it delivers noise here, this one would get colder and colder, so the temperature here would go down, the temperature here would keep going up, and that cannot possibly be the case. I guess it would be probably better if we made one a resistor, right? Yeah, if we make this a resistor, well, whatever. I don't know. Well, whatever, it's easy to show. They are noiseless, okay? Capacitors and inductors are noiseless. Now, beware that real capacitors, of course, they have leads, and the leads, for example, typically they will have resistor. They will be resistive. They're not superconductive, and so here, this part, of course, produces noise. So a real capacitor probably has some noise also, but the part that we really want of the capacitor itself doesn't. Okay, and the same thing for inductors. Now we come to noise calculation, and this is the more important part on this slide. Instantaneous noise voltages, they add together, right? So it's still true that if we had two resistors, let's say, with noise sources, here we have V1 of t. We don't know what it is, but I always can write this, of course, right? And so there would be a R1. And there would be a resistor R2, and it also, I model its noise. I know the power, but I'm writing here the instantaneous voltage V2 of t, right? Then, of course, I could model this thing with the new resistor R1 plus R2, and then a new noise voltage V1 of t plus V2 of t. And these instantaneous noise voltages, they just add together. Certainly KCL holds here. Right? The trouble is that because I don't know V1 and V2, well, it's kind of useless to know that. So let's try to figure out. We know what the noise power is, V1 square, right? And V2 or Vn2 square. We know these. Let's try to figure out what the Vn square of this one is. So that's going to be V1 of t plus V2 of t squared and mean. Okay, that is going to be equal to V1 of t squared and mean plus V2 of t squared and mean plus 2 V1 of t times V2 of t mean, no square. Okay, so the first two parts we know, that's going to be 4 kb times t times this one's going to be R1, and this one's going to have exactly the same prefactor, but R2 times b, right? So the first part we know. Plus, well, what is this thing here? Well, noise sources are uncorrelated. Noise sources in different resistors are uncorrelated. In other words, the electrons that are hopping around here, they don't know and don't give a damn about electrons hopping around there. They don't use cell phones. They don't communicate at all. So they're doing their they're jumping around totally randomly. That means that these two terms are really uncorrelated, and consequently this thing evaluates to 0. Okay. So consequently, the noise of this combined resistor is just equal to V1 square plus V2 square, right? So that's the V noise of R1, R2, with the total noise. Okay. Okay. Now we have to be extremely careful. Instantaneous noise voltages add. Noise power here adds also. But on the previous slide, given this example, I said, well, when I evaluate this 4 KB 4 KB times T times R times B, then usually I take the square root and I say that this is, for example, 4 nanovolts for a 1K resistor and 1 megahertz bandwidth, right? 4 microvolts. 4 microvolts in that case. So otherwise 1 hertz bandwidth. So, but this is 4 microvolts RMS. So if, for example, I had 2 resistors and this one here produces 4 microvolts RMS, and let's say this one was the same value, it also produces 4 microvolts RMS, then the combined thing produces how many microvolts RMS? Well, these, they don't add. It's the powers that add. So we have to square those, add them together, take the square root, and then we have the total power of the thing. So this is actually 16 plus 16 is 32, and the square root of 32 is square root of 2 times 16, so this would be about 6 microvolts RMS total, right? So we have to be very, very careful. Noise powers add, instantaneous noise voltages add, but RMS noise voltages don't add. Most common mistake made with noise. And it's totally wrong if you make that mistake. And the IC is not going to work, right, if you make that mistake. Okay? So try to remember this one. Okay, what else? What else? Okay, well, so actually this, so apparently if we have 2 resistors, figure out the noise of the compound combination of those 2 resistors, no big deal. Right? We actually can, and that's sometimes useful, we can actually generalize this principle to arbitrary RLC networks. If we had suppose we had a very complicated network with many capacitors and inductors and resistors and more resistors, right, and whatnot, right? And we look into this thing here, and we just want to know how much noise does this whole thing produce, right? Then, of course, we could now replace every resistor with an ideal resistor in series with a voltage noise source and parallel with a current noise source, and then obviously calculate this, right, analogous we did for the resistor. That would work. Would be a lot of work. A simple thing is to figure out what is the impedance of this thing. C of S is, of course, now a function of frequency, and that's going to have a resistive part, that is also a function of frequency, plus j omega, an imaginary part, right? A real part and an imaginary part, right? Like this. Then the noise, Vn squared, the total noise seen by this system, is going to be 4kT times R, function of frequency, times B. Okay? So apparently all we need to do is we need to calculate the impedance of this whole complicated mess of a network, which we know how to do. It's still tedious, but a little bit less tedious than dealing with 20 individual little noise sources, right? And then we take just the real part of it and put that into a noise equation. We know what the noise is. It's probably easy to prove also, but I'm not going to try. All right, so now we know about noise in resistors, and we know about noise in simple passive networks, RLC networks. Now, what about noise in diodes? First of all, noise in diodes, for some reason, is usually called differently than noise in resistors. It's called shot noise and not thermal noise, even though shot noise is a form of thermal noise. It's still got the zero mean. It's got a Gaussian PDF. We know now what that means. It's white. Its power spectral density is white, just like the noise from resistors. Proportional to current. Ah, wow, there is something new. See, the noise current of a diode, if we had a diode and we run some current through it, then really what we get is the diode current ID plus the noise current flowing through that diode. And the power, again our amp square power, of this noise component here is given by this expression. And it is proportional to ID. So in other words, if you have a diode and you don't run any current through it, then you don't get any noise from it. Oh, good. Different from a resistor. So it's proportional to current, so that's somewhat different. And it's independent of temperature. I made an example here. If I have a diode, 1 milliamps away, 1 megahertz bandwidth, I get 17 nanoamps RMS noise. Okay, now there is this big confusion. Shot noise isn't thermal noise, and it has a different. This equation definitely looks different from for KTR, right? So, but if I go to the small signal space, then to the small signal model, then of course a diode is nothing but a resistor, right? So I could compare the noise from a diode, a small signal diode, to the noise from a small signal resistor, which is the same as the large signal resistor, of course. Let's do that. That's sort of interesting. So on one hand, we have here this RD, which is equal to VT over ID. That's the equivalent. That's the equivalent that's the equivalent resistance of our diode. Okay. So then on the other hand, here we have our resistor. That's just the value R. Okay. Now. Now here, we in parallel have our noise current source, and the noise current is going to be IDN square is equal to 2Q times ID times B, right? And here we also have, now we are going to use also noise current, IRN square is equal to 4 KB times T times 1 over R times B. Let's set these equal. No, let's do something else. Let's set RD equals R. Let's suppose that we are in a situation where we just need a resistor of a certain value, and we want to decide, should we rather use a diode or should we use a real resistor for our resistor to make that resistor? And would there be a difference in terms of noise? Reasonable question, huh? Okay, so then we can rewrite this 2Q times ID now is equal to VT over RE over RD, and VT over RD is also equal to R times B. Right? So now I can write this 2 times Q times KT on Q times 1 over R times B. Right? This is equal to 2 times KB times T times 1 over R times B. Now we compare. This is the noise from the diode. This is noise from a resistor. And what do you see? It's almost the same, short of a factor of 2. The diode wins by a factor of 2 in terms of noise power. It's remarkable. The whole rest of the equation is exactly the same. So why does a diode produce more noise? Well, I went to ask the physicists, and they had a very wonderful explanation. They said, oh, it's not in thermal equilibrium. Now, whatever this means, apparently, if I have a thing like a diode and I run current through it, and in order to really make up my resistor RD, right, then that thing is not in thermal equilibrium because I force this current through it. And then this whole 4 kT noise equation doesn't apply anymore because I'm pumping power or current into the thing. And so this 4 kTr equation consequently also is off the mark. And so here apparently it seems to be off the mark by a factor of 2. It could be any other thing. If you wanted to, suggestion for a startup company, if you wanted to, you could make new resistors and sell them that had lower noise or different noise from resistors that you now buy from DigiKey or whatnot, simply by making a circuit that that looks at the voltage. You make a box, right? A resistor really is kind of a box, if you want, that has 2 leads, right? And inside you have a voltmeter, right? Measures the voltage, and then you also have a current source, and you run a set amount of current that is proportional to V, determined by, and you figured out what V was, determined by your instrument. Now, however you put this current source, you're going to get a lot or a little or whatever, a certain amount of noise. In the end, that may be just the noise so that this appears like having 4 kTr noise, but it could be more. Most of the time it's going to be more. But if you're good at it, it can actually be less. Right? So you could certainly make resistors that have less than 4 kTr noise, and maybe people would come and buy them from you. What do you think the problem is? Actually, this is not an uninteresting thing. Because if, of course, we could build resistors with less noise, we could build circuits with less noise than we ought to get, and then because noise is seen as linked to power, we could presumably make circuits with lower power. Great, huh? Well, the reason that doesn't work is that all this junk that you get to put into this box needs power. So either you put a battery into the box, or you add a power supply, right? And so that the whole neat idea goes out. And I have never completely formally proven this, but in the best cases, I found that when I synthesize all of this, I just stick as much power in here as I'm going to save out here, thanks to having a lower noise resistor. But in reality, because my circuit here isn't perfect, I use a little bit too much than the optimal power, and I'm actually going to be losing. So fortunately, we figured that out before a poor guy was doing his PhD on this thing, only to find out 5 years later that, sorry, you can't do that. If you find a way, a lot of money there, a lot of fame, anything you want. Yeah. Okay. MOS transistors, they are also noisy. And I have 2 noise sources. Again, this thermal noise source, and then this flicker noise. Let's start with the thermal noise. So the MOSFET, and here really I should be drawing a small signal model. Well, why don't I do that? Right? So GM times VGS for out. Let me leave away all these capacitors, they're noiseless anyways, right? Well, just one of them. Okay, so what are the noise sources here? Well, this guy here is really the big one. The channel is really, I mean, if we put the transistor, of course, in saturation, it acts like a current source, but the channel itself is a resistive thing. And so we would expect it to exhibit thermal noise, and lo and behold, and it does. So the model for the noise that's flowing in this channel is a current source that is in parallel, and so that would be the drain noise is 4 kT times factor gamma times GM times delta F or B or whatever like that per bandwidth. So a couple of things. Well, so this is again pretty much the equation that we have. What about this gamma? Well, gamma in most textbooks you will find is 2/3 for a MOSFET. For a bipolar it would be 1/2. So actually that's again right. If you use a MOSFET to synthesize a resistor, then you apparently get only 2/3 as much noise as you would be getting from a normal two-legged passive resistor, but then you would have to stick in power to make it a resistor, and it would be nonlinear. So, sometimes in practice you find that this gamma factor is a little bit larger, and so I often, also because I just hate to write 2/3 all the time, I often make it 1. There are also papers in the literature that say, oh, we've measured this for our process and it's like 10. Well, if you find such a process, then look for another foundry. In the meantime, we found out that, yes, it's possible to get a gamma of 10. I don't know how and why, but they somehow mess it up in the foundry, and there are plenty of other ones that don't. So if you get one that has an excessive gamma, just choose another one. What about this resistor here? Does it have thermal noise? Well, it doesn't have thermal noise because there isn't really a dissipation mechanism associated with it. That's only this effect that the amount of current that flows in our transistor varies a little bit as a function of VDS. This is really only a modeling resistor, and as such, it doesn't have noise. Okay, thank you. I take that. And then the capacitor, we know it is not noisy, but what sometimes is an issue is, of course, the gate is poly. Maybe it's silicited, but nevertheless, it's going to be resistive. And especially in RF circuits or so, at the antenna impedance or so, maybe 50 ohms, or if you have a transformer, maybe even lower. And then we add here another 20 ohms or so. Well, we get really significantly extra noise. So in those cases, you actually find transistors that are laid out, again, as fingers, lots of fingers. Very short, stubby gates. They are tied together on both sides, strapped with metal, and so the sort of really the effective resistance of the gate is minimized. So you've got to be careful about stuff like this. Probably not for most of what we're doing in this course, but if you do the right or wrong thing with the transistor, it may matter. Right, and there are a bunch of other things that sometimes do matter. Okay, yeah. So of course, if for yeah, if our FET had a gate current, then we would have IG would be 2Q F, right? And we would have this in addition. Fortunately, up to now, this gate current still is, forget it. Maybe 5 years from now, will no longer be true, and we will have an extra bloody noise source to deal with. Huh? Okay. So that's for our MOSFET. We can model it. Model its thermal noise essentially by the thermal noise from the channel. And then there is this flicker noise business. Turns out that if we were to somehow measure, and we're going to do that afterwards with SPICE, the noise current over our MOSFET as a function of frequency, and we do this log scale, here also log, then we would get here this 4kT 2/3 GM delta F, right? Over that, right? Oh, out here, so this is actually delta F. But at low frequency, you would find that we get excessive noise, and this excessive noise at low frequency is called 1/F noise. Apparently, what it's caused by is the electrons or whatever, holes or electrons or whatnot that are supposed to travel through the channel of our transistor. They just can't do a simple thing. I get from here to there or the other way. Somehow it must be very pretty in that channel, because sometimes they go a little bit and then they get stuck there and they wait a little bit and then they flow on and they finally come out, right? And because of that, of course, sometimes you get a little bit too little current because that guy really decided not to come out just yet. And then later when he finally comes out, we get a little bit too much current. And that's a pretty slow process. Speak microseconds and often much less than that, right? So they really take their time. And so we have this problem here. This frequency depends on the size of the device and technology and so on. We'll calculate it later. Maybe 10 kilohertz to megahertz or so, something like that. Right? Yeah, so it can be a problem. It also depends on the process. So first of all, there are simple. Well, if you can zoom in a little bit just to this. Okay. So there is a simple model that says what the 1/F noise is as a function of frequency now, because it's not white, and a function of technology and device sizes. So it depends on KF. This KF is a technology parameter, and for our technology, I've listed what it is here, and that's often the hardest thing. When you get a technology, you know that the devices probably have 1/F noise, right? All of them had so far that I've used. But how much do they have? Well, somebody's got to measure it, and many foundries, they don't measure it. Moses and so on. So they set this in SPICE to 0, which is again nice, but when you then build the circuit and get it back from the fab, it wasn't quite 0, right? So this parameter, you somehow need to get it from somewhere. And then it apparently depends on the current. The more current, the more noise. It depends on the size of the transistor, and it depends on the oxide capacitance. And again, this 1/F noise thing, because this noise is at low frequency. One thing is that the PMOS devices usually have less noise. And the generic explanation is that in a PMOS device, the field in the channel is such that the carriers, the holes, they actually go away from this interface between the channel and the oxide, and apparently that interface is particularly interesting for the for carriers to get tracked, and consequently, if the interface is cleaner, you're going to have less noise. Right? So, or if actually in the PMOS, if they don't get that close to that interface, there's smaller chance that they get stuck. Right? So PMOS usually less noise. Native has even less noise, typically. What is a native device? Well, it's a device that has not received any threshold voltage adjustment. So an N-channel device usually will have about 0 volt threshold voltage, and increasingly those are available in modern technologies. They have a mask to do that. Probably not for this reason, but we can use it. So sometimes if we need really little noise, then the native device may be little flicker noise, then the native device may be attractive. Okay. One of the funny things with if you can change the zoom again, please, thank you, is this 1/f thing, right? So of course at very high frequency, 1/f is 0, and we don't get any 1/f noise. We get all thermal noise at high frequency. That's fine, but what happens at f equals 0? Well, making a little example here, I calculate the entire flicker noise from a lower frequency, f low, to a higher frequency of 1 megahertz. Okay, so basically I integrate this equation, and I get this for the integral. And of course, if I make f low, the lower integration bound to 0, this thing blows up, and I get infinite amount of noise. But what does it mean, making f low equal to 0? Well, it means that we go back in history, back to eternity, past the Big Bang. I mean, really, back forever, right? That's just a little bit unrealistic, right? I mean, should we go back to the beginning of humanity, back to when the IC was made, back to when the power was turned on? Well, I have here an example. I went back to 1 hertz, so 1 second I went back. And then I get like 700 picoamps RMS noise for that example. And then I went back all the way 1 year. Right? I ran my circuit for an entire year and was listening all the time and was collecting the entire noise power over that entire year up to 1 megahertz. Right? And then I get 1,000 picoamps. Now, granted, it's a little bit more, but it's not a whole lot more. See what happens is that if we look at this thing on a log scale, log here also, and here we plot here this ID 1/f squared, it's going to look something like this. Okay, and here is 1 hertz, and here is 1 year. And all we did is we started with the 1 hertz case. We started with all of this noise. Right? Well, actually, we didn't include any thermal noise. So we integrated up to here. Let's say this was 1 megahertz. Right? And then when we switched from 1 hertz to 1/a year, then we added this sliver here. Well, big deal, right? Big deal. Actually, that's not true. That's not true. This is if I had put it on a linear scale, right? And this actually looks then sort of strange, but on a linear scale, of course, 1/a year and 1/a hertz, they are just next to each other. Okay, so that's why really the lower integration bound doesn't matter a whole lot. Use a hertz or use 1/1 if you want to play it safe. In California, power goes out anyway, right? So you don't need to worry about it. And then if you go back far enough, right, it's really like an offset, right? If it's DC, it's like an offset, and so we should really talk about offsets then when we sort of make it a year or since the IC was made. Okay. Let's continue with this next time. So if you haven't done so already, please turn in the homework.